Just as we spent the first several units understanding the derivative and what it tells us about a function in a particular instant, we are going to, in this unit, begin understanding the definite integral and what the process of integration or working with a function called the antiderivative tells us about a function over time. So for today, we're going to learn about the definite integral and Riemann sums. So if you consider the situation at the top of page 69, where we have velocity given at 50 miles per hour, if we were to graph a constant velocity of 50 miles per hour over a time interval from 0 to 5 hours, well, we know that constant velocity would just be a horizontal line if we're graphing velocity with respect to time. And if we travel at this velocity from 0 to 5 hours, our delta t, or change in time, would be 5 hours. And we know that this line up here, v of t, would equal 50 miles per hour. So we know distance, we know how to calculate distance given our velocity, and we could multiply that by our time. Or since our velocity is constant, we could just reason 50 miles per hour for 5 hours is a total distance of 250 miles. So what you might notice on this graph is that when we look at the area between the velocity function, so between the line and the t-axis or the x-axis, we have a rectangle. And when we calculate the area of that rectangle, well, the height of the rectangle is 50, and the base of the rectangle is 5, and 50 times 5 is 250. I also know that, like, if I multiply 50 miles per hour times 5 hours, that we get 250 miles. So there is a connection with understanding how our position changes or how our distance changes, and understanding how that relates to the area under the curve of a velocity graph. So we're going to explore the definite integral. And when I say area under the curve, because I know I'm going to say that a lot, to be very clear, what I mean is the area between the curve, or in this example it was a line, but it's usually a curve, and the x-axis. Because if our curve is beneath the x-axis, the area isn't really under the curve, it would be above the curve. When we talk about the definite integral, we're talking about an area. And when I read this statement and I see this kind of, it looks like a long S, that actually comes from the idea of a sum. So when we are looking at the notation for a definite integral, a and b are boundaries. These are values of x. F is the function, and dx, we could think of that almost like we do when we take a derivative, that we're looking at this with respect to x. But what we'll learn, and we'll go a little more into this later, but dx represents the width of the rectangle or trapezoid or whatever shape I'm calculating. And dx is kind of like delta x, except that it's going to be infinitesimally small. As I write that, I'm like, oh my goodness, how do I spell this word? Infinitesimally small. So what I mean by that is it's so small that it's almost nothing, and we'll get into that. So if we go back up to this example with the rectangle that we just did, this 250, this was our height, like this was our v of t, or in this case, f of x. This delta t, that was 5, so we said 250 was our height. Delta t is like our dx, or in this case, it would be like a dt. So if we think about how we calculate the area of a rectangle, this kind of corresponds to the height, this to the width, and those values a and b in this last example would have been t equals 0 and t equals 5. So they correspond to the boundaries on the, in this case, t-axis, where we're calculating that area. So as we work with the definite integral, you will get a deeper understanding of it, and we'll talk a lot more about that idea of infinitesimally narrow rectangles as we go on. Okay, so in all of these first examples, if we're finding the area of the definite integral, we have to, for today, if we're not using Riemann sums, which we'll get to in a minute, we have to use geometry, and we have to know what this graph looks like. So for this first example, if I imagine the graph of 2x minus 5, I know that it has a y-intercept at -5, because I could think of this being a function that is linear in slope-intercept form, 2x minus 5. I know the slope is 2, and what we're trying to evaluate is the area between the function and the x-axis from x equals 1 to x equals 5. So it might help us out to the side to know those values. So f of 1 is 2 times 1 minus 5, so -3. F of 5 is 2 times 5 minus 5, so 10 minus 5, which is 5. And then lastly, I might also want to know where it crosses the x-axis. So I could solve and get 5/2 for that. Okay, so if we sketch this graph, I know that when x equals 1, that this function is at -3. So I'm just going to say that's -3. When x equals 5/2, so 1, 2, 3, 5/2 would be 2.5. It's going to be crossing the axis. And then when x equals 5, so 3, 4, 5, it's up at +5. Okay, so, oops. All right, so that is, it's a line. It looks like a line. That's what our graph looks like. So if we're finding the area, I'm going to back up to this note that's under the box under definite integral. So when the area that we're finding is beneath the x-axis, we're going to consider it negative area, and that'll be really important going forward. So as we calculate the area from 1 to 5 between the curve and the x-axis, or the line and the x-axis, I notice that from 1 to 5/2, the area is beneath the x-axis, and it makes a triangle. So I've got to remember how to find the area of a triangle. I know that's just 1/2 times the base times the height, or base times height divided by 2. So the height of this triangle, so to speak, that's going to be our -3. And the base of this triangle, well, from 1 to 5/2, 5/2 minus 1 gives us 3/2. So even though I said -3, we're going to consider that just a 3 for the height. So 1/2 times 3/2 times 3, that is 9/4. But remember, we said that area under the x-axis is negative, so I'm just going to call that a -9/4. Then if I look at the area above the axis, so from where at x equals 5, where we're at 5, 5 on our curve, back to where x equals 5/2. Now we're working with positive area. So 1/2 base times height. The base of our triangle from 5/2 to 5 is 5/2. The height of our triangle is 5. So 1/2 times 5/2 times 5 is 25 fourths. So something that we will go into more detail in section 5.2 is properties of integrals. But something we can do is, I'll just tell you now, is we could split this integral up into two integrals that are getting added together. So instead of from 1 to 5, we could think of this from 1 to 5 halves. We're integrating the function 2x minus 5. And then we're going to add to that from 5 halves to 5. We're integrating 2x minus 5. So those areas we just got, this first one, that's our negative 9/4. And then that second area is the 25/4. So instead of considering this as one shape, we decomposed it into two triangles, and that's what those two integrals represent. So now when I add 25/4 and negative 9/4, we just get 16/4, which is 4. So our final answer is 4. All right, this next example requires us to remember something from geometry. I guess we're required to remember quite a bit from geometry, but to understand the first part of this piecewise. And if this doesn't jump out to you right away, I don't necessarily expect it to, but know that we're going to see these quite a bit. So in this next example, we are evaluating 3 different definite integrals. And for the problems we're working with today, we have to know what the graph looks like. So of the piecewise function, the second and third piece are linear, but this first piece is something that I think year after year students kind of forget that you actually do know what that looks like. So I'm going to go out to the side for a second, and I'm going to write y equals, way out to the side, y equals the square root of 9 minus x squared. And I can tell by looking at this is a function. Whatever I plug in for x, I'm only going to get one y value. But you might not notice, or you might not make that same observation. This might not look like something you know from geometry, but let's look at what happens when we square both sides. So y squared is just y squared. And then when we square a radical, since those are inverse operations, we now have 9 minus x squared. Now this maybe still doesn't look like something you recognize, but let's add that x squared to the other side. And when we do, we have x squared plus y squared equals 9. And if you recall from geometry, the equation of a circle is x minus h squared plus y minus k squared equals r squared, where h comma k represents the center. So if we have an x squared and a y squared, this is a circle that is centered at 0, 0. And since the radius squared is 9, the radius is 3. So if I just think about what that looks like, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We made that last radius really long. All right, so that is the graph of this circle. But going back to what we started with, y equals the square root of 9 minus x squared. This is a function. A circle is not a function. It does not pass the vertical line test. So what we really have when we take the square root of y from the circle equation, remember that when we take the square root of a variable, so like if I came back to this step and took the square root, I always want to consider the positive and the negative square root. And these two parts of the equation represent the semicircles that make up the circle. So the one that we started with is the top part. All the y values are positive. So 9 minus x squared, we could plug in any number between a -3 and a 3 for x, and we're going to get a positive number or 0. If we stick that negative out in front, that gives us the bottom. Okay, so that was a quick geometry refresher. I think it's worth our time because you're going to see semicircles sometimes. I don't know. I don't know if I want to say often, but sometimes. Okay, so now we can sketch this piecewise function. I know I've got to start at -3, and then just looking at the different integrals I've got to evaluate, I need to go out to at least +10. So again, this is just a sketch. So we said from -3 to +3, we have that semicircle. So I'm gonna call that the first part of our piecewise. From 3 to 5 on our x-axis, we have the function x minus 3, which is linear. And so if I just plug in a 3 for x, 3 minus 3 is 0. So I know that this function is continuous at 3 because from the left and right, we're at y equals 0 or g equals 0. And then I could think of this as having a slope of 1. So as I go over 4, 5, we're going up 1, 2. And it might be helpful to like write some points down. So this is the point 5, 2. I think the other ones are pretty clear where we have zeros. This is, of course, 0, 3. All right, so that's the second piece of our piecewise. And then the third piece, 12 minus 2x, is also linear. A y-intercept of 12, a slope of -2. If I plug in the 5, 12 minus 2 times 5 is 12 minus 10, which is 2. So we're still starting from this point 5, 2. So we know it's continuous. And now if we're sloping down, for the rest of this graph, I'm just going to sketch this, but our slope is down 2. So this part's steeper. And like, I'm just going to call this a 10 out here, because we just need that coordinate. And so at g of 10, and again, the reason I'm going to 10 is I just looked at the problem and I saw I need to go to 10. So if I plug in a 10 there, 12 minus 2 times 10 is -8. So that's the point, 10, -8. Okay, so when we are finding these areas, when we're evaluating these definite integrals using geometry today, we're going to learn another strategy in just a second. Still geometry, though, for today. We need to look at our boundaries. So for the integral in part A, we're evaluating the area between the curve of G and the x-axis from -3 to 3. And if I look, that's just my semicircle. So I know the area of a circle is pi r squared. In geometry, you learn to calculate sector area, and a semicircle is a sector that's half the circle. So the area of a semicircle is just 1/2 pi r squared, or pi r squared divided by 2. And then if we need to find those quarter circles, we could just divide it by 2 again. So this entire area that I'm shading orange, if my radius is 3, 3 squared is 9, that whole area is 9 pi over 2. And that's what we get in part A for our definite integral, 9 pi over 2. All right, in part B, we're starting at x equals 0 and moving over to 5. So in part B, we said that the orange shaded part of our semicircle is 9 pi over 2, but since we're starting at 0, we're going to need to know how much is in this quarter circle. Well, that's just half of 9 pi over 2, so that's just 9 pi over 4, or the area of the full circle, 9 pi, divided by 4. But we also have to now include this little triangle from x equals 3 to x equals 5. So again, we know the area of a triangle is base times height divided by 2. The base is 2, the height is 2, so the area of the triangle is 2. So when I combine these areas from x equals 0 to x equals 5, I'm adding the area of a quarter circle and a triangle. So I could just leave that 9 pi over 4 plus 2, or you could call that 9 pi plus 8 over 4. However, if you wanted to get common denominators, I'm not too worried about it. Okay, lastly, in part C, we're asked to evaluate the definite integral from x equals 0 to x equals 10. And so we already know the definite integral from x equals 0 to x equals 5. We know that's 9 pi over 4 plus 2. So I could think of that I'm really adding like 9 pi over 4 plus 2, but I'm going to add that to the integral from 5 to 10 of g of x. Okay, so we still have a few more areas to figure out. This triangle, this narrow triangle that exists above the x-axis, has a base of 1, a height of 2. So its area is just 1. And then lastly, we're left with this triangle that's below the x-axis that goes to 10. So if we look back about where this crosses the x-axis, it crosses at 6. And if you're not sure, you could set this equal to 0, right? Like 12 minus 2x equals 0. So 12 equals 2x, so x equals 6. So that's the 0 of that function. And so the triangle that I'm looking at has a base of 4, because it's from 6 to 10, a height of 8, and we said we're going to consider that area negative. So 1/2 times 4 times 8 gives us, 16? But we're going to consider that a negative 16. Okay, so the integral from, oops, I don't know how that just happened. If we evaluate this integral from x equals 5 to x equals 10, we have this area of positive 1 minus this area of 16. So to answer part C, we just have to put this all together. 9 pi over 4 plus 2 plus 1 minus 16. That's just 9 pi over 4 minus 13. Okay, so that's an introduction to evaluating the definite integral using essentially decomposition of geometric shapes. So decomposing shapes we don't really know into smaller shapes that we do know, like semicircles and triangles.